This is lab 5 EE542 modified TCP/IP kernel stack for fast and reliable file transfer. I am Kaishavi Umrethwala and I am representing it along with Aditya Venkat Ramanan. So, when TCP flows are sharing a congested link, the exponential backoff algorithm is appropriate algorithm to deploy. However, we know that reducing the sending rate and window may not be the proper response under lossy link conditions. So our goal is to improve performance, means the throughput of traditional TCP by modifying congestion control mechanism for high latency and lossy link, such as satellite or long range wireless uplink. We have a client server model as a network. We test the custom TCP IP by using the standard FTP program, which use SCP command to move a 1 GB file from one node to another. Losses and latencies are inserted into the links and explore the performance of custom TCP IP. So here are the results of traditional TCP IP kernel stack. The link is of 100 Mbps and the total delay of the network is 10 milliseconds, and we haven't employed a packet loss yet. So as you can see in the picture that we are getting 11.4 megabytes per second throughput. This is the table which were made by changing RTT delay and packet loss. So we can see that as we are increasing delay and packet loss, the throughput is decreasing. And from this graph, we can see that the throughput is decreasing exponentially when delay and packet loss is increasing. So our approach for the custom TCP IP kernel stack is as proposed in the paper by Amit and Alexander, that removing exponential backup from TCP altogether can be done without inducing any stability side effects. As long as the endpoints uphold the implicit packet conservation principle, they can only improve their end-to-end performance relative to the exponential backup case. So here's the principle. We need to fulfill this requirement that RTO should be always greater than RTT. We have used the Jacobson's algorithm for computing the RTO as suggested in the paper, which is RTO is equal to SRTT plus 4 into variable RTT. So we have used Vano and Hybla congestion control algorithm to improve TCP throughput along with removing exponential backup. So Vano monitors the network congestion level and uses that information to decide whether the packet losses are likely to be due to congestion or random bit errors. It is widely used in wireless local area networks, which has lossy links. It improves TCP Vegas algorithm by employing threshold to check status of the network for congestion. And Hybrid is especially used for high latency links such as satellite or long range wireless uplink. It is designed to address some of the negative effects of long network RTT. It addresses the issue of slow congestion window increase and removes the reliance on RTT from the congestion window algorithm. So this is done by adjusting the size of the congestion window to a normalized ratio of the previous window, which results in a larger average congestion window. So here we have modified the following files, which consist tcp.c, tcp underscore kong.c, tcp underscore hybla.c, tcp underscore input.c, tcp.edge, tcp underscore minisocks.c, tcp underscore output.c, tcp underscore timer.c, tcp underscore vano.c. So I'm going to brief you regarding the major changes of these files. So in tcp.edge, we have set the maximum TCP window to 65535, which is the maximum sequence number one TCP segment can handle. Then we have set the fast transmission threshold. It is the number of duplicate acknowledgement which we receive, and then after we start retransmitting that particular segment, then we have set the TCP sync retries to 5. This is the how many retries we can do when we are setting up the TCP connection. TCP RTO maximum value uh, is set to zero point 0.6 seconds. Our TCP RTO minimum value is set to 0.1 second. TCP timeout initial value is set to 0.2 second as given in the research paper. And we have set the window scaling to 6 rather than 3. Here we have turned on the Nagel algorithm, which was default turned off. We have set the initial congestion window size to 1000 rather than 10. Here is the formula to calculate RTO value, which is calculated using Jacobson's algorithm. Now we will move to another file, which is tcp.c. Here we can see, as we don't want exponential backup algorithm, so we have removed all those things which affects the or include that algorithm. So we are removing timeout, descaling from this both function, and we are setting up the upper bound of the congestion window to the TCP initial congestion window. Same as here. Now we will move to TCP underscore timer.c. Here, as we don't want exponential backoff, we are ignoring the timeout and returning 0 from this function. We have disabled the ping pong mode. Here we are calculating RTO using the Jacobson algorithm, so we can uh, fulfill the implicit packet conservation protocol principle. Now we'll move to TCP underscore vino.c. Here we are increasing window size every time plus 3 rather than increasing only plus 1. So we can achieve our desirable throughput faster. Now here, if there is no congestion, then we are keeping the window at its upper bound. And if we found any congestion, we are not backing off, we are keeping it the window as it was. We'll move to the another file, which is tcp underscore output.c. Here we are keeping the new window size to the maximum TCP window. We are not decreasing the window size, we are ignoring all those elements which employ exponential backoff algorithm. We have set the window size to its maximum here, which is 65535. In tcp underscore kong.c, we are not descaling the window size by 2 as it is done in exponential backoff algorithm, since we want to remove that algorithm. In tcp underscore hybla.c, I am setting the window size to 1, initializing the sender window size to 1, and initializing the upper bound of that window size to 6250. So we don't create congestion in the network, because in Hybla, the new window size depends on the previous window size rather than RTT. Here, in Hybla congestion avoidance, we are not decreasing the window size. and keep it the same. In TCP underscore input dot c, here also we are not decreasing the window size to remove exponential backoff, and we are initializing the TCP window size to the upper bound as its initial window size. And at the last, TCP underscore minisocks.c, we are setting the sender window size to the upper bound. So these all changes will add up and will give us our desired throughput, which is more than traditional TCP congestion control algorithm. So further explanation will be given by Aditya, which is the execution of this algorithm.
Hi, I'm Aditya, and I'll be covering the rest of the demo video. I'll be talking about the kernel compilation steps, and I'll be showing the actual objective where we have to set our network settings to having an RTT of 200 milliseconds and with a packet loss of overall packet loss of 40%, and trying to achieve at least 10 megabits per second performance with the modified TCP/IP kernel stack. So before we make changes to any TCP/IP, what we have to make sure is that we have sufficient storage space in our machine and at least a 1 GB swap size of physical memory. And after that, we could then go ahead and check out the kernel code from the Ubuntu repository. And depending upon what version we are running, we have to make sure that we check out the version that is closest to our version. Less, but closest to our version. After we do that, we make all the TCP/IP changes as part of the objective, like the stuff that Kaishavi went through in the first half of the video, and then we install the libraries required for building this new modified kernel, and we'll be building this with a method called incremental build, which basically uses a makefile process, and this is significantly faster than the traditional way that the Ubuntu suggests, and because we could add more cores to this build and it's much faster. And once the build is complete, when the compilation is complete, we get Debian packages created, and these Debian packages can be then installed in our machine, and we could then make changes to our grub bootloader to tell the bootloader to boot to my new kernel, the new modified kernel, right? So now I'll show what I've done is these are the Debian packages that I talked about, and this is the data.bin file. That's the 1 GB file, just to be more precise. As you can see, this is the 1 GB file that we are supposed to send, and these are the Debian packages that we need to install. Same on the server side. So we are using the same network topology, client, server, and router, and I've already transferred the Debian packages to both client and server. And as you can see, we don't have the data.bin file yet. So we are supposed to send this file across using the SCP protocol, using a modified kernel. So I've already installed the kernel and I'm already booted into the kernel. So how do we know that we have booted into the current kernel? Using this command, we can make sure that we are using the latest kernel. So earlier, this was 4.4.0 hyphen 114, which is the default on AWS on an Ubuntu 16.04 LTS. So we do the same here as well, just to make sure that we are booted into the updated kernel. So this marks our updated kernel, right? So this matches with the file name, that the Debian file name. So now the first thing we have to do is to set our network. We set it as 100 megabits per second. latency as 1 microsecond, and burst to be 901,555. Oops. So I made a couple of mistakes here. So first of all, our internal network has been signified by ETH1 interface uh, of the instance. So you have to make sure that it's ETH1. And second mistake is I added a show here. That's why it was throwing an error. So we do the same thing here. I'll just copy this there. Right. So just to make sure that it's correct, we run the qdisk show command. And as you can see, the speed, the burst, and the latency has been set. Now we do the same thing in the wireless router as well. Qdisk add add dev with 0 root handle 100 megabit, latency as 0.001 ms, the burst as 901,555. We do the same for ETH1 as well. So because our router will both of the interface ETH0 and ETH1 interface of the router instance is part of the internal network, we are supposed to make it consistent so that the speed is uniform throughout the link. And we do that here. So we'll run an iperf just to check we are getting the desired speed. See 10.0.2.199. This is my IP address for the server. And you can see here that we are getting a 100 megabytes throughput for the interval of 10 seconds. So we can make sure that the speed is correctly set. So we'll do one thing. We'll also try the iperf in the UDP mode to check the bandwidth. Minus C 10.2.199. I'll specify the bandwidth as 200 so that we could get the actual bandwidth. So we should be getting around a 50% loss with the two if we are setting bandwidth as 200 megabit. Yeah, so as you can see, the bandwidth is actually 97.6, which is close to 100, and bandwidth is around. Yeah. So with those in place, we'll go ahead and set the delay and the drop. So this is the code for that. Qdisk. So we need an RTT of 200 milliseconds. So we set 100 milliseconds in both the E0 and the ETH1 interface. And we are setting drop 20% on both the interfaces. That means we would have on an average 40% packet loss over the entire network. Oh, I misspelled parent. Oh, I didn't give a space. Sorry for that. There we go. So now we do this again for ETH1 as well. So as you can see, the cursor movement is staggered, so I can sort of signify that the delay and the loss is added because my elastic IP address is on the 80 interface. So these are some of the sort of an idea that you can get that the configuration settings have been set properly. Yeah, so as you can see the delay there. Yeah. So we have 100 milliseconds and lost 20% on our router, so over the entire network. So to RTT is 200 milliseconds and the overall loss is 40% loss. Now we'll do a ping command. We'll send 100 packets for an interval of 200 milliseconds to our server just to see that the RTT and the delay has been set. We do the same for server as well. We'll ping client from the server minus 5.2, 10.0.1.177. That's the IP address from my client. And yeah, so you can see here that the packet loss is around 37% packet loss, and the RTT average is 200 milliseconds. So this is the sort of ping statistics for our desired network setting. And on the server side, you can see almost similar. We have a 40% packet loss here, and we see a 200 milliseconds of delay. So now what we'll do is we'll set the TCP congestion control algorithm. So we'll be showing Hybla and Vino for our demonstration purposes. Let's go congestion control. Set that as Hybla. Oh, I need to give this root privileges. Sudo. There we go. Now we do the same here as well. C, command V. Yeah. So just to make sure that the congestion control algorithm has been set, we use this command. Net for So as you can see, currently Hybla has been set. We do the same on the server side. Oops. And there you go. So now we run the SCP. So we need to use the .pm file because we're running it on AWS and it's across the instances. What file are we sending? We're sending .bin. And where are we sending? Ubuntu 10.0.2.199. Where do we want this file in the server? We want it here. Ubuntu EE542 lab 5. So just to make sure that the file doesn't exist, I do a delete command and on the server side, and then I'll run this. So as you can see that the transfer has begun, and right now it's at 2 Mbps, but it's dropping. But this is going to take some time, so I'll pause the recording here, and then I'll resume once it's done. So it just finished transferring the file, and as you can see, we were able to get a 1.6 megabytes per second as our throughput. And just to check whether the sent file was correctly sent, we use the md5sum command to check the checksum. So data.bin, and you can see that if the checksum matches, then it was able to send it correctly. Yeah, so now you can see that the checksum completely matches. So now what we'll do is we'll set our condition algorithm to be vNow. Yeah, so here we'll set it as vNow, and we'll do the same there as well. And then we'll do the cat thing again. Cat command. We can make sure that that's we know. We look at again, and just to make sure that we don't have a copy, we delete the previously downloaded this thing so that we don't have it right now, and we run the SCP again. So this is the SCP command, right? Same thing, same steps. So same as before, I'll pause the recording here because it's going to take some 10 minutes of time roughly, and I'll then resume the recording once it's done. Yeah, so it just completed transferring the file, and you could observe a throughput of 1.4 megabytes per second, which corresponds to 11.2 megabits per second. Right, so we do the same thing. We run md5 sum to check the checksum, see whether that matches. md5 sum, data.bin. So we do md5 sum to check whether the data was sent reliably. There isn't any data corruption. Yeah, so as you can see, we were able to send the file reliably. So as you can notice that for 200 milliseconds RTT and 40% packet loss over the network, for Hybla we were getting 1.6 megabytes per second, and for Vino we were getting 1.4 megabytes per second. So we see that it's a significant improvement from what we traditionally had in our TCP/IP protocol. And that concludes the demonstration. Thank you.